So welcome to the fundamental of computer vision. Just to review some of the stuff that we mentioned earlier with the A multiplied by B in the cross product scenario. We have the matrices will be like that. And I mentioned last time that this A multiplied or cross product by B can be written as a multiplication of two matrices. And this will be this guy. I call it like, let's say like matrix A, and this B will be that guy. So the cross product by itself, this can be decomposed to these two matrices. But just for your reference, this matrix is a rank 2 matrix. This matrix is a rank 2 matrix, and we'll understand why this is useful a little bit later today. This is a rank 2 matrix. What does rank mean? From your linear algebra class, you should already knew that the rank is the number of independent columns in my matrix. Yes? So if I have 3 independent columns, let's say, meaning that each of these columns is giving me a new equation. And it does not depend on any of the previous equations, because if it does depend, so you actually doesn't give me any new information. You don't give me any new information if you just give me 3 equations, but one of them depend on the other. What does it mean depend on the other? Meaning that it's just multiplied by 2. So if I'm giving you 2x plus 2y equal 4, and then I multiply the whole equation by 2, and I give you another equation, do you consider this new equation is really new information? It is nothing. It is just depending on the previous equation, so it does not add any information to me. But if I have from these 3 columns or 3 rows, 3 different independent equations, I can say that this matrix is rank 3. If you give me 2 independent and the third is dependent in any of these, so I can say like this is rank 2, because it just gives me 2 useful equations, 2 information. If you give me 3 columns, but 2 of them depend on this third one, so you actually give me 1 information, and that's why it will be matrix of rank 1. So with this matrix, I'm telling you that this is rank 2. Okay, we'll see like why this is useful later on today. Just to remind you again, if we were like to have like a rigid transformation between the x and x dash, so this x will be translate and then rotate, and then this x will be landed on x dash. Also, we showed that t, x, and x dash, we mentioned that these vectors are coplanar, and we already explained what does coplanar mean. Coplanar meant that they are in the same plane, or they are parallel to the same plane. If I have that, t cross product of x will give me a vector that is perpendicular for both. If I multiply this perpendicular by the vector of x, let's say, or a transformation of this vector x, all of these transformation will be perpendicular to that, and that's why I have 0. Because the cross product, if 2 perpendicular vectors will give me another third vector that is perpendicular to the plane. But if I multiply this perpendicular to any of the vectors that is basically light in that particular plane, it will give me 0, because the dot product between 2 perpendicular vectors is 0. Okay, and then we showed last time that this is equal to 0, and say like, okay, if I would like to map this point x to what we call the epipolar line, we just need to multiply this x by a matrix called E, which called last time essential matrix. It will give you the L dash, which is the epipolar line in the other image. Suppose that you have a camera here. This is the image plane for the right camera. Suppose you have another camera here with this center of projection. Then you have like another image from the left camera. And we would like to say, or to get a relation between the point here and a certain particular line there. And the E will hold for that particular transformation. Remember that this is not homography. Homography, we are translating from a point to a point. But here we are translating from a point to a line. which called constrain. I'm constraining that this point should land in anywhere in this particular epipolar line. Why this is useful? Because it will make the search later on useful to get the correct point. But the assumption that we already had earlier when we mentioned this equation, that the points align to camera coordinate axis, meaning calibrated camera. So all of these points is calibrated to the camera. In another sense, I know the intrinsic, let's say. I know the intrinsic relationship, just like to go back one step, again, to remind you about the intrinsic and the extrinsic. Intrinsic holds the relation between the image plane and the center of projection of the camera. This is intrinsic. Extrinsic means, or hold the relation between the center of projection of the camera and the whole world, the 3D world. So in order to go from the 3D world to the image, I will go from the 3D world to the center of projection of the camera, and then from the camera to the image. And I mentioned last time why I put the image plane in front of the center of projection while it should be in the back, because this makes math easier. Practically speaking, the image plane should be like behind the center of projection, but the image will be flipped. Yes, and you will have minus f, the focal length. Now I transfer this f to here just to make mathematical easier, and the image will not be flipped. That's all. Okay? And that's why the transformation is from here to here, and then from here to the image plane. But this image plane now is there. Okay? And we mentioned that in order to do this to this, I don't know exactly if this is or this or this is the point in the real geometry. That's why all of these will map to that line. We also mentioned that I have here a certain particular point called the epipole. And this epipole has a certain particular nice feature that all of the epipolar line need to intersect in this point. In another sense, if I were to use this is here EE, the answer should be 0. We also proved like how we can get this E matrix when we took the coplanarity equation and then just plug from the rigid motion what is x minus t is. Here I have x minus t transpose. I know the x minus t. We proved last time how we can get this, which is particularly that, multiplied by this. We just showed that this cross product can be transferred to the multiplication of two equations. And we just do the math correctly. And I have x dash transpose x, and these, we call it the E. The E is a rotation and the translation. What does that remind you with? Extrinsic. Yes, the extrinsic parameters, because the extrinsics, what we did earlier is just like a translation and the rotation. This is the extrinsic, to go from the 3D world to the center of projection of the camera. So the essential matrix, in another mean, its implicity contains the extrinsic parameters. Correct? Remember that this E is the product of these two. Remember that what I told you about this earlier? Matrix, rank 2. Correct? So the E will be a rank 2 matrix multiplied by whatever the rank is. So if you multiply for your reference a rank 2 matrix by any other rank, what should be the results? Or any other higher rank. So if you multiply a rank of 2 multiplied by a rank of 3, what should be the result? Or the rank of the result? Okay, so then we have this x dash transpose Ex is equal to 0. X dash transpose from here, x dash is something in the right camera or the right image of that camera. X is in the left side. Correct? So I'm relating this stuff by this equation. So here the dash in the right, so we can say like this is right and this is left. Okay. We also showed that x transpose, as we have seen from the previous slide, this is equal to 0. Earlier, also in the previous slides, we showed that X transpose L is equal to 0. If this is the case, the dashes will be also equal to 0. And L dash is equal to EX, which I already showed you here. But if I would like to map a point to the line, I have to multiply this by E. And I told you also, if we were to multiply this E capital or the essential matrix E by the epipolar, which is here, just give you 0. Because all of the epipolar line would just match to only certain, or intersect at only certain point. If you were to think about that, meaning that there should be like a certain particular point on the left, per se, in the image or in the whole wall, that always will map only to one point. This is only happen at the epipole. Because this point, for instance, can be this or this or this or this. All of these lands in different places here, correct? If you were like to have another thing, it might be like that. If you were like to have another point here, it will be like another epipolar line, correct? But if you were to think about all of these, usually they have like a certain particular point that only one, which is the epipolar. That's why the essential matrix multiplied by that X multiplied by this particular point should be equal only to 0. But we mentioned that how we can generalize to uncalibrated camera, because all of these equations, we have assumed that we have a calibrated camera. In another sense, we know the intrinsics. We know the relation between the center of projection and the image plane. We know this. Correct? What you need to do is just like the essential matrix, which is something of the extrinsic. How about we would like to even generalize that with the fundamental matrix, which we assume the cameras are no longer calibrated. They are not calibrated. I don't have any information in advance. I need now to relate the image pixels to the image pixels or to the line pixels. Okay. Just to remind you that with this essential matrix, we have these equations, but the assumption, we have a calibrated camera. Okay, that should be fine. So I am relating the right and the left through this, give you 0. So the essential matrix operate on image point expressed in normalized coordinates. Points have been aligned or normalized to the camera coordinate. So now, if I were to have the image plane and I have the camera coordinates, how they were earlier be related to each other? If I were to have an image point and I have a camera point, so an image point and then a camera point, what was the relation earlier? If you recall, if this is where to be an X and this is X cap, X is equal to K X cap, correct? The intrinsic parameters, do you remember the K? Yes? Going the other way, so X cap will equal to X inverse X, correct? If I were to work with the left image, for instance, I would like to get a relation between my image plane and my center of projection, or the camera. So I have to work with the K matrix. If I would like to get the camera point, it would be just the K inverse and then multiplied by the K image point. So now I have the relation between the image point and the camera point. The same exactly when it applied to the left-hand side of the camera, it should be also applied to the right-hand side of the camera, or the other camera, I meant. So if things applied here between this and this, also I have a relation between the points in the pixels here and the center of projection of my camera, correct? But does the relation between this and that should be equal between the relation between this and that? Meaning if I have K here, should I also have K here? Or if I have K here, this should be K dash, since I'm working with the dash, so it will be like, I can call this K right and this K left, for instance. Should I use K right and K left, or should I use just K? Of course, there is no guarantee that both will have the exact same k. I don't know. That's why this k to the power of -1 should be k dash, or k that is in particular to the left side, if the other one is the right side, and so on and so forth. We need things even to be more general. It might be in some cases that they are exactly the same, but there is no guarantee that they will be always the same. That's why you have to use like a little bit general case. Okay, so plug these variables to this equation. X dash transpose, meaning I need this transpose, this transpose will be not but X dash transpose multiplied by K minus 1 transpose, which is K dash minus transpose, as you can see here. This E will remain the same, and then the X cap will be this, which is this. Do you know that AB transpose is equal to B transpose A transpose? If you don't know, this is the case. Okay. So plug everything here. I have the dash, I have the X, and the matrix E is multiplied by the K dash minus transpose, and then the K inverse of K. Basically, this is what we call the F matrix. So the E matrix refer the caps, which is the camera points, because they are calibrated. But the F relate the image points to the right and the left together, which is the pixels. So this is the difference. It's exactly doing the same job, but now I am related to the pixels instead of just like the camera points. Because in the previous case, it is calibrated. Now I didn't assume that this is calibrated. But remember, again, the F depend on that. And this E, if you recall, it was a rotation and a translation, correct? And from this T with the cross product I mentioned earlier, that it is rank 2. So I know now that F should be rank 2, not rank 3. Even if it is a 3 by 3 matrix, but it is rank 2. So F maps pixels to epipolar lines, correct? So going back to the equation that I just showed you, when X dash transpose EX equal to 0, what we need to do with all of these is just remove the E and put the F. Remove the E and put the F. Remove the E and put the F, and all exactly will be whole. Again, all the equations will be correct. Okay. So just like breaking down the fundamental matrix to these particular things, which is depend on both the intrinsic and extrinsic parameters, because this E, if you recall, holds the extrinsic parameter. This K holds the intrinsic parameters, correct? Even if I didn't explicitly depend on that, but at the end, it shows also that this fundamental matrix is decomposed from intrinsic and extrinsic parameters as well. Okay, so sounds good. But now the question is how I can solve for F. How I can get F. You are telling me that this is equation hold, but I need to get F. How I can get F? We need what we call the 8-point algorithms. How is that? Assume that you have M matched image points like XM to XM dash, XM, X1 to X2, X1 dash, X2 to X2 dash, and each correspondence should satisfy this particular equation. Okay, how you solve for the 3 multiplied by 3 F matrix? Again, the magic, the SVD. Everything we have solved so far till now with the singular value decomposition. How we can do that? As we mentioned earlier, we just need to set up the homogeneous linear system with the 9 unknowns. I have like with this F matrix, 3 by 3, F1, F2, F3, F4, all the way to the F9. I have 9 unknowns. Please create this matrix with these 8 points, because we mentioned earlier, if this have the 9 unknowns, it might end up with just 8 unknowns because I can't divide by the last one. Yes, if I divide the last one, so I just scale everything. It's not always quite correct, but this can be like a relaxation a little bit for my equations. But the question now, how many equations do you get from one correspondence? So here with this equation, if you do the multiplication, you will get just like from this y and x and y, you will get just one equation. So basically, for each correspondence, you will get just one equation. And since we need 8 equations, so we need 8 correspondences. But there is also an intuitive way to understand that. Earlier in the homography, we mapped a point to another point. And from each point correspondence, if this is correspond to the other, will give me x and y. So it will give me 2 equations. So in order to solve 8 equations, I just need 4 correspondence in the case of the homography. Because for each correspondence, give me 2 equations. Now I have 8 equations. But in this case, intuitively, I am mapping a point to an epipolar line. So I'm mapping a point to a line. If I make a point, mapping a point to a line, I'm just getting 1 correspondence. I haven't the possibility to get 2 equations, just 1 equation. Accordingly, I need 8 correspondence to solve 8 equations. And here is the math speaking. When you do this multiplication, you just get 1 equation from that, not like the others. Before, we have like 2 equations with the homography. Okay, so do set up the homogeneous linear equations with these 9 unknowns from F1 to F9. And we mentioned that we can divide by the last one for instance, then I will have only 8 instead of just 9. That's why I need 8 equations. So just here to remind again, each point pair is just 1 scalar equation because the epipolar constraint is mapping a point to a line. So now I have what they call the 8-point algorithm. I have to have 8 correspondence in order to solve that. From here to there, it's just like, again, a multiplied by x is equal to 0. Correct? Because this is what I have, a multiplied by x equal to 0. How I can solve for x? Singular value decomposition. How we can get that? The singular value decomposition will solve this x as the eigenvector of the A transpose A that is corresponding to the smallest eigenvalue. Which means I would like to minimize this subject to this constraint. I have already explained this in details in previous lectures, so please go and review that. So SVD will solve this. So just like to put things in like a steps in order to solve for this 8-point algorithm, normalize the points and then construct the M multiplied by 9 matrix A. Find the SVD of A. Of course, the entries of F are the elements of column of V corresponding to the least singular value. Or the other sense, another explanation, we'll get just the eigenvector corresponding to the smallest eigenvalue. We'll show a little bit later today also like an example in MATLAB. Things will be a little bit more clearer for your imagination. Then after I do that, I will have the F. But I didn't force the rank 2 constraint of F. So what I need to do is just force the rank 2 constraint. You can see why is this in this reference, but I've also give you a hint why F should be rank 2. Because it depends on that matrix multiplication, and one of these matrices is basically rank 2, and then unnormalized F. How we can enforce a rank 2 constraint on F? So now we solved for the F. How you will force that this F is not rank 3, this is rank 2. The information that you are getting from this is not 3 independent equations, it's just 2. How you can force that? SVD again. How we can do this? This is what we'll show you mathematically and then using the MATLAB. So now I am giving a matrix F. Please find the matrix F dash of rank 2 that is closest to F, or for rank K, for instance, if we would like to make it general. I have the F. I have calculate. I got like the F right now. So I will do another singular value decomposition for just particularly F. So F will be equal to U sigma V transpose. How I can force this F to be rank 2? Because if you decompose that, you might get this sigma like this, sigma 1, sigma 2, and then sigma 3s, and all of these will be zeros. So these are the singular values of my matrix F. If I'm giving you a matrix like that, and I'm telling you that this is not rank 3, this is rank 2, how you will force that? Intuitively speaking, just like to get a sense of the relation between the singular values and the meaning of the rank, basically, if I will remove the value that was here and force this to be 0, so I'm just getting 2 information only. So I am forcing that matrix to be 2. And if this is 0, right now it is rank 2. And when I get the eigenvector of the smallest eigenvalue, it will be for this smallest one. But I have forced that to be only 2 instead of 3. If I'm telling you that, no, I would like to force this to be 1, then this is also need to be 0. Yes? So if I'm giving you any matrix, just generally, F or whatever the thing is, and this is like very big matrix with k elements, and I would like it to be forced to be k minus 1. So this means that I will just remove the last one I will substitute the last one to 0, then I'm getting like rank minus 1. If I'm getting the last 2, so rank of k minus 2. If I'm removing the 3, then k minus 3, and so on and so forth. Because I'm forcing that. I'm forcing to remove some of the important information, yes? Or some of the information. But I know in advance that is not important, because I'm telling you, we already knew that F should be rank 2. So I will create this new matrix with this sigma dash, which has the sigma 1 and sigma 2 only, without the sigma 3 or with the sigma 3 equal to 0. So just like to summarize, the essential and the fundamental matrices are 3 multiplied by 3 matrices. They just encode the epipolar geometry of 2 views. Given a point in one image, I will multiply it by the essential or the fundamental matrix. It will tell me the epipolar line, and this is what we already mentioned, all of this, just mapping a point to a line. It can map that using the essential matrix if it is a calibrated camera, or it can map that through the fundamental matrix if I don't have a calibrated camera, which is uncalibrated. Finding the left and right null spaces of E and F tells us where the epipoles are, because we said that E multiplied by E is equal to 0, or F E is equal to 0. So this E is not but the null spaces of that. So just like to summarize, the essential matrix works with calibrated camera or the in-film plane coordinates, but with the fundamental matrix, I'm working with the pixel coordinates in another sense. Okay, so now we have an example which we will solve it, showed you like how to do that in MATLAB. So in this example, we have, for instance, like all of these epipolar lines, and assuming for that we are matrix F here is like this. And you have this point X. And we need to see what is the mapping of the epipolar line to the other image, or to the image taken with the other camera. Where is the epipolar line in that particular place? We will apply this exact theory that we just derived. You have the point X multiplied by the fundamental matrix. It will show you the epipolar line. This is what we have just derived. We said that the fundamental relate a point to the epipolar line, correct? You have multiplied this point by F, it will give you the epipolar line in the other image, given that you know F. For whatever reason, you just got to know F for whatever like reason. So multiply this X by this F in MATLAB, you will get actually this vector. This vector is not but L dash. L dash is what? It is the epipolar line in the right camera, or in the right image. So this will be the L dash. So this is point is mapping to that particular epipolar line from the other side. As you can see from here, the camera take this image from this side, but the other camera takes this same building, but from the other side. And we would like to map where is this here. Where is this, sorry, in that image? We have epipolar constraint, which is only constraining that particular point to be in that particular line, correct? Okay. Where is the epipole then? How you can compute for the epipole? We know also that f multiplied by e is equal to 0, correct? Because e is the null space of f. We already also proved that. We know that. How you can solve for e? You know f. I'm asking you what is the null space of f, or how you can get e. This is homogeneous linear system, by the way. How you can solve that, as we mentioned, SVD. How you can do that in MATLAB? We said that this, in order to solve something like that, a multiplied by x is equal to 0, I will go to get a transpose a and then decompose it to eigenvalue decomposition. And then we'll take the eigenvector that is corresponding to the smallest eigenvalue, because this guy will show me, let's say, sigma 1 actually squared, because this is multiplied, sigma 2 square, and then sigma 3 square. And this will be multiplied, let's say, like by the v, 1, 2, 3, or maybe like transpose, 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 whatever the shape that you would get. Then this guy will be multiplied by the last one, correct? I will take that eigenvector, because this eigenvector corresponding to this smallest eigenvalue. Because we mentioned earlier that it will be ordered in a decreasing scenario. Sigma 1 is greater than sigma 2 is greater than sigma 3, and so on and so forth. So I'm getting the eigenvector of the smallest eigenvalue of A transpose A. So this means that I have to get F transpose F. And after I get F transpose F, I have to solve for the eigenvalue, or the using the MATLAB for this, in order to get the eigenvalues and the eigenvectors. And then I will take the eigenvector that is corresponding to the smallest eigenvalue, and I say like, this is E. There is also like a small trick that we will also use it just like in the next couple of slides to show you what is the exact correct values of E. But just conceptually speaking, this is what we need to do. So we will do the eigs of F transpose F, as I mentioned. With this, it will give you the eigenvectors and the eigenvalues. So U is the eigenvectors, and D will be the eigenvalues. With this eigenvector, you have the first eigenvector, the second eigenvector, the third eigenvector. With these eigenvalues, it will give you the first, the second, the third. We will take the one that is corresponding for the last one. So this is my vector. This is what I'm trying to always say. Solve for the eigenvalue decomposition of A transpose A. Take the vector, the eigenvector that is corresponding to the smallest eigenvalue, and this will be your null space solution. Okay, so now we will get that's corresponding to this. The eigenvector associated with this is just that. In MATLAB, in order to choose this, I have to say if this is U, you will take U with any row, but just the third column. Yes, this is in MATLAB, syntax in MATLAB. So I'm just choosing the third column, and basically the third column is like that. If that's all, this is my E. Remember that the epipole projected to image coordinates. So then how we can get our E with the image coordinates then? With this, we need to get this projected to the image coordinate, and meaning that we need actually to normalize that to the last coordinate, yes? And that's why we need actually to divide by this value. If you divide by this value, now I have my correct E. So this will be, this will be the epipole, okay? So now we'll switch the gear to a new thing which is called stereo. So now we finished like what will be the relation between like 2 points correspondence using the homography. We have also take the triangulation, which is both estimation. We know the x and the small x and then the small p, and we need to know like where is the x capital in the 3D world, and we showed like how we can do that. We also took the fundamental and the essential matrix to map a point to an epipolar line constraint. We now need to go to further something called the stereo or stereo rectification. So if I were to give you these two images, what is the difference between these two images? So this is the first one, this is the second one, going back and forth. Yeah, so this is the image to the left and then the image to the right. What are the difference? This one is here, this one is there. If you look closely at that, and given what we have already just showed you that we have two cameras, you might think that one of these are from the left camera and the other image is from the right camera. And when you flipped between just them, you feel that there is a moving, correct? While the image actually is constant. Try to do this by your eye. Yes, because you have two cameras. One right camera and one left camera, yes? But they are just in the same plane, yes? They are not like merged together. They are just in the same plane, yes? But literally speaking, you have two cameras. Do like that to looking at the same image and then look like that, you'll feel like it's kind of moving. Try to do this, you will feel like it's kind of moving a little bit. And this is what we exactly hear. And if you calculate actually the difference, you'll get something called disparity, which is basically difference like in depth between the right and the left. So the amount of horizontal movement is inversely proportional to the distance from the camera. In another sense, if you are like coming closer to me, yes, and then I begin to do this right and left, and there is another one that is actually even further, which I will recognize more these disparity things, yes, the one that is a little bit closer. So it's inversely proportional to the distance. And more formally, we have actually to reconstruct that to prove what is the relation between the right and the left one according again to the math. But intuitively, what we will do if you just like begin to shift between one eye and the other eye, you'll begin to see the things are moving while they are actually not moving at all. They are just like in the same exact place. Try to play with these things until we explain mathematically how things are related to each other.